dressing up y equals x squared. So basically we're looking at the base function y equals x squared for a quadratic, and we're looking at all the transformations, how we can change it to get any type of parabola. So the graphs of all quadratic functions are related to the graph of the basic one, y equals x squared. These graphs are the result of transformations to the graph of y equals x squared. This investigation examines the effect of three types of transformations. So back in Math 8, I think it was, you talked about some of these types of transformations, but more to do with shapes as opposed to actual equations. So multiplying x squared by a number. So some examples are y equals 2x squared, y equals negative 5x squared, y equals 0.5x squared. Then we could add or subtract a constant to x. So that would be inside the brackets, and then square that. Or we could add or subtract a number outside of x squared. So we're going to examine the combined effects of all three. Some examples are given there, okay? And this is a form of a quadratic that we're going to use a lot, okay? It's actually called the vertex form of a quadratic because we're going to be able to tell what the vertex of the graph of that parabola is. When you get to Math 30-1, you're going to do a whole ton on transformations, a whole unit, and then every function that you learn about, you're going to transform. So this is just the beginning, okay? So complete the table for y equals x squared. These points will be the key points we'll use all of the time, and then graph it on the grid. So negative 3 squared is 9, negative 2 squared is 4, 1, 0, 1, 4, 9. Remember, when you square a negative, you get a positive. So graph that, these points. Okay, join them up as best you can. And really, you need to memorize what y equals x squared looks like. You shouldn't have to do a table of values. You can do it in your head. 0 squared is 0, 1 squared is 1, 2 squared is 4, etc. So it's a parabola. This is your base parabola. The vertex is at 0, 0. Symmetrical about the y-axis. Okay, so this is a parabola. Coordinates of the vertex are 0, 0. There's your vertex. Equation of the axis of symmetry, as I just said, is the y-axis, which has the equation x equals 0. Okay, so now we're going to do some transformations of that. So it's the effect of a on y equals ax squared. So there's a demonstration. I'm not going to do that right now. Basically, we can look at our graphing calculator. So we would do that if we didn't have access to a graphing calculator. Basically, if we put in, I'm going to clear off what I had in there. I'm going to put in x squared and graph on a standard screen. Okay. Now, what happens if I put in, y equals, if I put in another function that's 2x squared? Look at it. Okay, it still has the same vertex, but it's skinnier. Okay, it's actually for every x value. So that original x value of 1 has a y value of 1, but now it has a y value of 2. So you've taken the original y value and you've multiplied it by the a value, whatever number's in front of it. So does changing the value of a change the position of the vertex? No. In general, what effect does a have on the graph? So it affects the width of the graph, okay, how wide it is, which is really based on stretching it. It can also affect, and possibly, the direction of opening. Because if it was a negative, so for example here, if I go and I put in another function, let's put in negative x squared, and I graph that, it's the same as the original except opening down. It's been reflected in the x-axis. So as the absolute value of A increases, so that means if A was negative, make it positive. So looking at just the value without the negative sign, what happens to the graph? So that when I changed the A value to a 2 from a 1, it got skinnier. So we say it just gets skinnier or narrower, we might use. So if A absolute value of A is greater than 1, then the new graph is narrower than the original. And we say we have a vertical stretch by a factor of whatever the absolute value of A is. So we never include a negative in this. If the absolute value of A is less than 1, so that's something like 0.5 or 3/4, okay? Then it's going to be wider. And if you're not sure, you could graph that as well. So we could go here and put 3/4 x squared. So blue was my original, and now the purple is wider. Okay. And now we have a vertical, so we still call it a vertical stretch, even though it's going wider, and we still call it by a factor of absolute value of A. It's just what the result will look like. When A is positive, the parabola opens up. When A is negative, it opens down. We already looked at that. So on your calculator, graph y equals x squared, negative x squared. We've done that. 3x squared and negative 3x squared. How do the graphs of both of them compare? Well, we've already done this part. Okay. What we say officially is that they are reflections of each other in the x-axis, or about the x-axis, or with respect to the x-axis. Okay, either of any of those. So now the graphs of y equals x squared, 3x squared, 0.4x squared, and 5x squared, and two others are shown. Label each one. So remember your base graph, look for that first. When x is 1, y is 1. So this would be your base graph. Okay. Then when x is 1, if we look here, this graph here has a y value of 3. So that's going to be y equals 3x squared. When x is 1, this has a y value of 5. So this is going to be y equals 5x squared. This one here is smaller than 1. Take a look. The only choice here, it's kind of hard to tell which it would be, but the only choice would be y equals 0.4x squared. I'm just going to erase that part there. Okay, so we've labeled each one, and then write the equations of the other two. So looking at this, these other two open down, and let's see if they're reflections of each other. So this one, when x is 1, always look, when x is 1, what's y? So it looks like it's negative 3. So it's the reflection of y equals 3x squared. So that's going to be y equals negative 3x squared. Put it here. And this one looks like the exact reflection of y equals 0.4x squared. So this will be y equals negative 0.4x squared. Okay. So I just labeled them there. So compare the points on the graphs of x squared, half x squared, and 3x squared with an x coordinate of 1. What do you notice about the y coordinates of each of these? Well, as I just said, that's what we were doing in the last one. The y coordinate is actually the coefficient. So here, this one had a y value of 5. That was the coefficient of x squared. Y value of 3, coefficient of x squared. So, what do you notice about the y coordinates of each of these points? The y coordinate is the same as the coefficient of x squared. Therefore, equal to a. Now, none of them were negative, so you could put in absolute value of A to make sure that you get it right. You don't incorporate the reflection as well. Okay, part C, the effect of P on y equals x squared. So when you subtract P from x, so some graphs are drawn there. They're labeled. Okay, are they congruent? That is, are they all the same size? So if you cut them out and move them over, are they the same shape and size? Yes. If P does not affect the shape and size, then what effect does P have on the graph? Well, those are the same shape, but they have a different vertex. So their location is different. Mathematically, we call it a horizontal translation. Okay. Take a look at the equations. So this has a vertex of 4, 0. This is x minus 4. So this original graph has been moved to the right 4 units, even though it says minus 4. So students get a little bit mixed up. Really, that new vertex, 4, is the value that makes this bracket 0. Because really, we want a y value of 0, right? So what makes x minus 4 0? 4 does for x. Here, what makes x plus 2 0? Negative 2 for x. So when there's a minus, you're going right. When there's a positive, you're going left and adding. So state the vertex of each of the following. So that was 0, 0. Just by looking at the graph, it's 4, 0. And here, negative 2, 0. Okay, but we've now talked about what happens. So now, using those patterns, if you have the graph of y equals x minus 7 all squared, what way are you going? Well, your new vertex would have to be what makes that bracket 0? 7. So it'll be 7 units to the right. Coordinates of the vertex are 7, 0. X plus 5 means you're translating 5 units, but now you're going to the left because negative 5 makes that 0. So the coordinates here would be negative 5, 0. And then parameter P translates the parabola horizontally P units relative to the graph of y equals x squared. So if P is a positive value, the equation will look like x minus P squared. The graph is translated to the right. Right? So if P was 5, this would look like y equals x minus 5 squared. Okay? If P is negative, then, so let's say P is negative 4, then you would have y equals x minus negative 4, which looks like x plus 4 squared. So you know it's going to the left. So the coordinates of the vertex are always P 0 in this case. Okay, so whatever makes this bracket 0. We always show it as x minus P. Rarely do we show it as x plus P. So you got to be careful on that. X minus P, the vertex is going to be P0. And then state the equation of each of these. So A, take a look at the vertex. It's at negative 4. So it's going to be y equals x plus 4. Because negative 4 has to make this 0. Then B, the vertex is at 1, 0. So that's going to be x minus 1. Okay. And then y equals, this is opening vertex of 3, 0. And so that's going to be x minus 3 squared. It's opening down, so we put a negative in front. Okay, so now we're looking at the effect of Q on y equals x squared plus Q. So that's where you're adding or subtracting something outside of the x squared. So take a look at these 3 graphs. They're labeled. Notice how they are in different locations. So the size, if you cut one of them out and moved it, it would be the same shape. The y's here have been kind of cut off. These are y equals. Okay, but different location. So are they congruent? Yes. If Q does not affect the shape and size, then what effect does Q have on the graph? Q
will be a vertical translation. So basically moving, move up or down. State the vertex of each function in the table shown. So here for y equals x squared, remember the vertex is 0, 0. Then look at x squared plus 3. Where's the vertex? It's at 0, 3. So the same y value as that constant. X squared minus 5, it's at 0, negative 5. So the nice thing about a vertical translation is you just have to look at that constant term that's outside of the x squared, and that tells you the y value at the vertex. So complete the statements. Graph of y equals x squared plus 8 is the original vertically, translated vertically. We're going up. Oops, we have to put the number of units here. 8 units up, because that's a positive 8. So the new vertex would be 0, 8. X squared minus 10, translated 10 units down because of the subtraction. So the vertex is 0, negative 10. In the equation x squared plus q, q translates the parabola vertically, q units, relative to the graph of y equals x squared. So notice the absolute values there. So that's just telling you how many units, and then based on the sign of q, whether it's up or down. So if q is a positive, so it looks like a plus a number. So let's say q was 5. This would be x squared plus 5. Then the graph is translated up. If q is negative, so it would look like this. So let's say q is negative 4. So it would look like y equals x squared minus 4. Okay, so that's down. So the nice thing about vertical translations is if it's solved for y, that constant term tells you your translation. So coordinates of the vertex of y equals x squared plus q, 0, q. So let's find the equation of these ones. Where that came from. So A, my vertex is 0, 5. So that's going to be y equals x squared plus 5. B, my vertex is 0, negative 2. So it's going to be y equals x squared minus 2. C, vertex is 0, 1. Now there's a little bit different here. It's opening down. So the x squared has to have a negative. Doesn't affect the 1. Okay, so when, especially in Math 30, you'll be going through transformations. There's going to be a certain order that you have to do transformations in, and reflections you would do before you do translations. Okay. All right, putting it all together. So all of these transformations together. So suppose you want to sketch the graph of y equals negative 2, bracket x plus 3 squared plus 4. How do you handle all three? So you have to first decide what each number represents. So what transformation does the 2 make? So remember that's a vertical stretch by a factor of 2. And then we always put in about the x-axis. Or actually, we don't always put in, but we should always put in. So any vertical stretches is about the x-axis. The negative in front, remember, is a reflection in which axis? So negative makes the original value, it changes the sign. So the original y value, if it was positive, now it's negative. So when you're changing the sign of y, it's reflecting in the x-axis. What is the plus 3 in there? Remember, it's opposite of what you would think. So you're actually going left 3 because negative 3 plus 3 is 0. So that's a horizontal translation. Of 3 units left. Got to get that in there. Plus 4 outside there is a vertical translation, and it is. If it's positive, it's up. Now, we're going to graph this, but in some steps. And then we're going to learn how to graph without having to do it in multiple steps, because we don't want to have to take the time to do that. So I'm going to minimize this a little bit. Okay, so, oops. Gotta go left here. There we go. Okay, so graph the function in 4 steps. So first, plot the key points of y equals x squared. So you have to memorize this. So 0, 0, 1, 1, 2, 4, 3, 9 will fit on there. And then the reflection, because remember it's symmetrical. Okay. So now we're going to do a stretch by factor of 2. So that means when we take our original y values, we multiply them by 2. So 0, 0 won't change. When x is 1, now y is going to be 2. When x is 2, it was 4, now it's going to be 8. And then we can't do any more than that. Then it's symmetrical about the y-axis, so it's going to look skinnier. Okay. So the resulting parabola, I say skinnier, but narrower is more mathematical. Let's talk that way. Okay. Then from there, we want to sketch y equals negative 2x squared. So before we had the 2x, y equals 2x squared. So we have that. I'm just going to put the points in. Now we're reflecting it in the x-axis, so the 0, 0 doesn't change, but this positive 2 becomes negative 2. Positive 8 becomes negative 8 for that same original x value. And then symmetrical about the y-axis, so now that's your new graph. So it now opens down. And then we want to translate every point. So now remember, your vertex needs to move, well, every point needs to move, but we'll start with the vertex. 3 to the left and 4 up. So 1, 2, 3, 1, 2, 3, 4, right there. Then I'll start with 1, negative 2. So I've got to, 1, negative 2 is there. I've got to go 3 left and 4 up. And then 2, negative 8 becomes 3 left and 4 up, and then it's symmetrical. So this is going to be here, this is going to be here, and then we can join them up. Translations doesn't change the size of them. Okay, so that took 4 different graphs. We don't want to have to do that all the time. Okay, so we're going to start practicing, and I'll show you a few little hints. Okay, so this one we're just identifying graphs, so that's a little bit easier. So take a look at some of the, you want to look at the vertices, right? So first one, x plus 8 squared. So the vertex there is negative 8, 0. So look for negative 8, 0. And there's 2 choices. This one, notice in front of the bracket, it's a positive. So that's going to be the one, this one here, going up. So that's going to be A. All right, next one, same vertex but opening down. So that's going to be this one. That is H. Next one, the vertex is negative 5, 4. So look for negative 5, 1, 2, 3, 4. Well, there's only one choice. It's opening up. From there, so that's B. And notice you could look for the stretch factor, but we only have one choice there, so that kind of made it easier. This vertex is 5, 4. So you want to go to 5, 4. Again, only one choice. That's G. And then this vertex is 2, negative 1. And there's 2 choices. One's narrower than the other. All right, so take a look at any other. This one's also 2, negative 1. Coefficient in this one's 1, and the other one's 3. So the bigger the coefficient outside of the bracket, the skinnier or narrower it is. So that means E is going to be this one, and F is going to be this one. Also, another way to tell, for 1 unit over, 1 up. Okay, so that means there's no stretch. 1 unit over, 3 up means there's been a stretch by 3. And then vertex here, -3, 2, -3, -2. So -3, 2, that's going to be D. -3, -2 is going to be C. Okay, so it's kind of easier when you have the graphs. You can narrow it down. Now we're going to describe transformations. So for each of the following quadratics, describe the transformations, state the coordinates of the vertex, and then accurately graph them. First one's been done for you, or almost been done for you. New parabola, so here, fill in the vertex. That's going to be +4, 5. So the new parabola is the result of vertically stretching by a factor of, so the coefficient there, you always take the positive, 3, resulting in a parabola that's going to be narrower than the original. Reflecting, that negative means you're going to reflect in the x-axis. And then you're going to translate the graph right 4 units and up 5 units. Okay, so let's graph that one. Okay, so because we know the vertex, let's plot it. It's 4, 5. Okay, then we know the shape of it based on the stretch factor. It's a factor of 3. So 1 unit over, 1 up would be your base graph translated, but it's going to be 3 up from there. As well, it was reflected, so it's going to be 3 down from there. And then it's going to be the same on both sides of that axis of symmetry. So with quadratics, you don't have to go through the correct order of stretches, reflections, and translations and show all the steps. You can actually think about, okay, what's the shape of it based on that stretch, what direction is it opening, and then move everything to that vertex and do it right there. So that's how I'm doing it because it's a little bit faster for you. Okay. Normally 2 units over is 4 up. Now, if we're multiplying by 3, that's going to be 12 up, and then reflected. Okay, so 12 minus 5 is 7. So from here, it's going to be down at -7. And then the same on the other side. Okay, so that's our first graph A. B, now I'm going to take the shortcut here by using some abbreviations. On a test, you cannot use abbreviations. Abbreviations, so we're talking about stretches, so vertical stretch by 2. Then we're talking about reflections, there aren't any. Then horizontal translation, 6 left, and vertical translation, 1 up. Okay, you cannot do this on a test. You have to show all the words. Vertex here is -6, +1. So let's graph that. We'll do it in a different color. -6, +1. 1, 2, 3, 4, 5. 1. Okay, it was stretched by 2. So normally for your base graph, it's 1 over, 1 up. Now it's going to be 1 over, 2 up, and same on both sides. For 2 over, it's normally 4 up. Now we're multiplying by 2, that's 8 up from there. So 8 plus 1 is 9. Okay. Then C, there's no stretches, but there's a reflection in the x-axis. That's that negative out front. And then a horizontal translation 3 left, and a vertical translation 2 up. Your vertex is -3, +2. So -3, +2. And instead of going 1 over 1 up, we're going 1 down from there because it's opening down. 2 over would be 4 up. Now it's 4 down from there. Then 9 down from there. Okay. And then back. -3x squared. We'll go back to blue here. So vertex, there's nothing added or subtracted, so it's 0, 0. So this has a vertical stretch by 3, and then a reflection in the x-axis. This is actually a little bit easier. So 0, 0, 1 over is normally 3 up, now it would be 3 down. Both sides. And then 2 over we would have is normally 4 up, multiplied by -3 is -12. We actually don't have enough space on our grid here. Okay, and so this would be D. And then this one, the vertex would be 2, -1. It's a vertical stretch by 1/2. No reflection. Horizontal translation 2 right. Vertical translation 1 down. Okay, so vertical stretch by 1/2, that's less than 1, so it's going to actually look wider. Sorry, what was the vertex again there? 2, -1. So 2, -1. Now for 1 over, it's normally 1 up. Now it's only going to be 1/2 up. So estimate that. For 2 over, it's normally 4 up. It's only going to be 1/2 of 4, which is 2. There's more space, so let's do some more. So 3 over would normally be 9 up. Now 1/2 of 9 is 4.5. So 2, 4.5. And then graph that. And that is E. Okay. So to summarize, that's your vertex form of the equation. We'll have a vertical stretch factor of, well, A, but A could be negative here, so that's why we use absolute value signs. It will open up if A is greater than 0, so a positive. It will open down if A is less than 0, so a negative. It has a vertex at PQ, okay? It's always shown with a minus there so that it's easily saying P there. It has a vertical axis of symmetry with an equation of x equals whatever the x value is at the vertex, so P. Okay, and that's it.